Mirrors, Part 2. Here are your priming questions. I want to start this with a calculation so you can see how to use some of the equations that we started from the previous video. So if we have a 2 centimeter high dragonfly that lands 15 centimeters from a concave mirror with a radius of curvature of 10 centimeters, where is the dragonfly's image and what is its image height? We are just going to find the location of the dragonfly's image. You are going to have to finish the image height before class by yourselves. So for this, we should be thinking of our equations. So we have our equation as the mirror equation, which is 1 over the focal length is equal to 1 over di plus 1 over do. And now we just need to list out our variables and figure out what we're doing. And so we have a focal length of, let me see, radius of curvature of 10 centimeters. If our radius of curvature is 10 centimeters, the relationship between the radius and the focal length is the radius is twice the focal length. So if we know that, we know our focal length is 0.05 meters. I'm going to go ahead and convert to meters. For the mirror equation, I would highly recommend for you to go ahead and change everything to meters. You don't have to, but I would recommend it in order to keep consistency between your problems and your numbers within the problem. Now that we have the focal length, we need to look at our di and our do and figure out which one is given to us and which one we are looking for. And so, if we go back to this problem, it lands 15 centimeters from the mirror, and so that's going to be the distance to the object, so 0.15 meters. And we are looking for where the image is located, so we are looking for our di first. And so, all we need to do is plug it into our equation. So 1 over 0.05 is equal to 1 over di plus 1 over do. When you work this out, you should get 0.075 meters. There you go. So you want to double check my work, and then from there, you'll want to see if you can find the image height using the magnification equation. We're going to go and move on for the video. Now we want to talk about convex mirrors. For convex mirrors, you can think of these sort of as the opposite of concave in terms of what they do to the light. For the concave, remember, we call these converging mirrors because they would converge towards the focal point. For convex, if we have parallel light rays that hit the mirror, they will always diverge. And for convex mirrors, they have a negative focal length. And the reason for this is because the focal point is actually behind the mirror. And so for us, our positive distances are going to be in front of the mirror and negative distances are going to be behind. And what you'll notice here is if we have parallel light rays, where they diverge, they will actually diverge from the focal point. So we could actually draw this dashed line showing a virtual ray, and then you can see exactly where these parallel light rays will be reflecting on a convex mirror. So, ray diagrams. For ray diagrams, we're going to keep this pretty simple. Okay, we're going to use the basic principle that we talked about for concave mirrors. So now we're moving a little bit backwards so I can show you how to draw these. For concave mirrors, the first ray that I always draw is the parallel light ray. And this is based off of the principle that we talked about in the last video. Parallel light rays, when hitting a concave mirror, will always reflect through the focal point. So you can see this one will go down here through the focal point. That would start out parallel, then through the focal point. The second ray is the second rule. It will go through the focal point, and then when it hits the mirror, it will reflect parallel. Now, where the two light rays that you draw intersect, that is where the image is going to be formed. And you can see that we always use the top of the image, the part that is the furthest away from the principal axis. And when we draw the image, that will be the same location of the image that we started from on the object. So that's why the top is over here. And in this case, we would say that this image is inverted. And you can also see that this image is also reduced. And in this case, it is a real image that is formed. So we could actually put a piece of paper here, similar to the lab that you should be working on now, and you should be able to project an image of this object. And this is for when the object is beyond the center of curvature. Now, when the object is at the center of curvature, it is a special case here. You'll notice that it's the same principle, parallel through the focal point, parallel. It produces an image that is at the center of curvature, and in this case, the image is inverted, but it is neither enlarged nor reduced. It is the same size, and it is still a real image. Now, as we go to between the center of curvature and the focal point, same principle for drawing our ray diagrams, parallel through the focal point, parallel. You'll notice that the image now is enlarged. It's much larger. It is inverted, and it is still a real image because it's on the same side of the mirror as the object. In this case, I'm going to go and skip what happens when the object is at the focal point, but we're going to address this in class, and I want to see what you think based off what we're talking about now and in just a little bit. Another special case here is when the object is in front of the focal point, or between the focal point and the vertex, or focal point and the mirror. The principles are the same, but it looks a little bit different. So in this case, we have our parallel light ray. When it hits the mirror, it goes through the focal point, and that one makes sense. The next one is the one that's going to be a bit more difficult to perceive. In this case, we have a virtual ray, which is indicated by the dashed lines, and it's as if it's coming from the focal point, so that this incident light ray is as if it were coming from the focal point to the top of the object, and because it's through the focal point as it's incident on the mirror, it will reflect parallel. And what you'll notice here is these two reflected rays actually diverge. And because they diverge, they can't form a real image in front of the mirror, and we have to try to draw what's going to happen behind the mirror. And so you'll see that we draw extensions of the reflected rays behind the mirror, and where those two reflected rays extensions as virtual rays, where those two intersect, that is where the virtual image is going to be formed. And remember, since this is an image that is behind the mirror, it is a virtual image. It's not really there. It's what our brain perceives as the image based off of the information given to it. This is just a quick diagram so you can see what happens. So the red arrows are going to be the objects, and the blue arrows are the corresponding images formed by these different locations. And you can figure out whether it's inverted or upright, whether it's enlarged or reduced, and whether it's a real or a virtual image. And what I want you to pay attention to are the trends. So what happens as you're beyond C, or at C, or between C and F, or between F and the vertex, or at the focal point. And that's what we're going to also discuss in class. Now for convex mirrors, the ray diagrams are very similar. We start with a parallel and a ray that goes towards the focal point. But the thing is, because we have the mirror in the way, our ray towards the focal point is stopped by the mirror. It can't actually go to the focal point. And what happens is they are reflected off of the same principles that we were talking about before. So the parallel light ray is now reflected, but rather than towards the focal point, it is away from the focal point. And the light ray that was going towards the focal point, it now reflects parallel. And you can see that these are diverging, and anytime our reflected rays diverge, that means we need to draw our virtual rays, and we will be forming a virtual image. And so what we have here, these are the virtual rays that are extensions of the reflected rays, and our image will be formed here. And so this would be our complete image. And so this image, the way we would describe it would be, this is a virtual image. It is reduced, and it is upright. It has the same orientation as the object. And here is a better look overall of 7 different positions and their corresponding images formed with convex mirrors. Now, here are some trends that I want to start you off on, and I want you to think about the negatives of these as well and what that means. So here we have positive focal length, concave mirror. Positive distances are going to be in front of the mirror. Think about what this means for virtual images and what their distances are. And these two that I've starred are commonly confused. So a positive magnification does not mean that it is enlarged. A positive magnification means that we have an upright image. As you do more calculations and see what happens with the magnification equation, you will begin to see this. So a positive magnification is an upright image, whereas a magnification greater than 1 is going to be an enlarged. And this can be either 1 or -1. This is just the absolute value. So if the magnification value has an absolute value that is greater than 1, it's an enlarged image. If it's positive, it's an upright image. If it's negative, it's going to be an inverted image. And hopefully you'll see that as we do our ray diagrams and our calculations. Here are some other concepts that I want to quickly talk about. A diffused reflection. And this is when the light is incident on a rough surface. And when that happens, you can see over here, the light is reflected in many different directions. And this is more of a scattering of light. So when we talked about colors before, and we talked about how the light rays are scattered by specific atom sizes, this is really the scattering that we're talking about, this diffuse reflection. This is why it goes in all directions, because the surface itself is a rough surface. Whereas if we were to have a perfectly smooth surface, the light rays would completely obey the law of reflection and would only go in those directions. The other concept that I wanted to quickly talk about is reverberation or reverb. For those of you that know anything about guitars and different sound effects that you can have with audio systems. And this is a big issue for people that are developing large auditoriums. They have to think about the acoustics and what it will do to every different person in every different seat. And so reverberation is caused by this reflection of sound and the person hearing it, hearing the different reflections at different times. And so as we have the sound being reflected off of all of these surfaces, it changes the time that the person hearing receives those sounds. And so it sounds like you have these echoes that are repeating one after another. And depending on the type of room that you have, these can eventually go away. And depending on the frequencies and the properties of the room, this will determine the rate at which it goes away. And here are your priming questions again.